Electrolytic cells are a different type of cell than we've been talking about with the voltaic. So a voltaic cell produces electricity spontaneously. So we have a spontaneous redox reaction that generates electrons, and the cell potential is always greater than 0. This is a requirement for voltaic cells. For electrolytic cells, this is a cell with a non-spontaneous reaction. The cell consists of 2 electrodes, which is the same as the voltaic. It also contains an electrolyte solution, so a solution containing ions, but most importantly, it has to contain an external power source. So this could include like a battery or an electrical outlet. The reason being is because it's a non-spontaneous reaction, we have to provide energy from an external source to force the redox reaction to happen. The other difference is that there is no physical boundary. So with the voltaic cell, we had that double line separating 2 solutions. In an electrolytic cell, we just have one solution and both electrodes are immersed in the same solution. So we don't have that porous boundary like we did in the voltaic. Okay guys, take a second to pause the video here and you can jot this down on page 41 in your workbooks. In an electrolytic cell, it uses a process called electrolysis, which we supply electric energy to force a non-spontaneous redox reaction. So essentially, we have to provide the electrons because they're not going to be transferred spontaneously. So if we take a look at the forward reaction here, we have reactants reacting spontaneously to give us products and electric energy. So that's the form of the electrons. If it's a non-spontaneous reaction, so if we want the reverse reaction to take place, now we have to provide the electric energy. So now it becomes a reactant necessary to force the reverse reaction. This is what takes place in an electrolytic cell. So if we take a comparison between the two, so I copied this into the workbooks. Most importantly, if we look at the spontaneity, voltaic cells are a spontaneous redox reaction. Electrolytic is non-spontaneous. Okay, another important distinction is that if we take the cell potential for a voltaic cell, it's always positive. For an electrolytic cell, we're always going to get a negative cell potential. At the cathode, gain electrons reduction. This is the same for both cells, so the SOA is reduced at the cathode. But the difference, the distinction between the two, is in the voltaic cell, our cathode is positive. Remember, cats have paws. But in the electrolytic, the sign is reversed. So our cathode now has a negative sign. At the anode, same for both. The SRA undergoes oxidation. So lose electrons oxidation occurs at the anode. But again, the sign is changed. So anode is negative for voltaic. In the electrolytic, the sign is reversed. The direction of electron movement is the same for both. So this doesn't change. It still flows from A to C. And the direction of the ion movement also is consistent between the two. So anions to the anode, cations to the cathode. A secondary cell can be used to illustrate the difference between an electric cell and an electrolytic cell. So essentially, as the cell discharges, so this means as it produces electricity spontaneously, it functions as an electric cell, a voltaic cell. An example of this is your cell phone battery. So in your cell phone battery, you have solid lithium, which the battery is made up of, and you also have a strong acid present. So we have H+ ions. If we look at the redox table, the OA is above the RA, and this is a spontaneous reaction. So as you use your phone throughout the day, you're producing electricity through this spontaneous reaction. If we want the reverse reaction to take place, however, so if we want lithium ions to react with the hydrogen, this is a non-spontaneous reaction. Now our OA is below the RA. And in this case, when it's recharged, so when you connect your phone to electricity, to provide that electric energy, the reverse reaction can take place and it will force the non-spontaneous reaction. So if we take a look at an example, what are the cell reactions and the cell potential of an aqueous potassium iodide electrolytic cell? So our first step is the same. We list out all the entities present and figure out what's our Ra, what's our OA. So in this cell, we have potassium, iodide, and water. Because we don't have any metals present, we have to use an inert electrode for the two electrodes, the cathode and the anode. And you'll also notice there's no double line here. So remember, for electrolytic, there's no physical boundary, no porous boundary. It's just one solution that contains both electrodes, aqueous iodine and liquid water. You could include potassium on this list as well. However, since it's a spectator, including it or not including it, either one is fine. So if we identify the OA and the Ra, we have potassium and water for OAs, and we have iodide and water for RAs. So our SOA is the water, and our SRA is the iodine. So here's our half reactions. Remember, gain electrons reduction occurs at the cathode. Lose electrons oxidation occurs at the anode. If we cancel the electrons, our net reaction is 2H2O plus 2 iodide gives us hydrogen gas, hydroxide, and iodine solid. The cell potential for my half reactions are listed here. So if we take the E cell value, remember it's always cathode minus anode, we get a value of negative 1.37. So the negative tells us that this is a non-spontaneous reaction. Okay, for voltaic cells, this value is always positive. Electrolytic, it will be a negative value. So if we look at another example, an electrolytic cell contains cobalt-2 chloride and lead electrodes. Here's the cell notation. So my two electrodes are both solid lead. And then in the solution, we have cobalt-2 ions and chloride ions. Again, there's no physical boundary here. It's just one solution. So if we list out all our entities present, including water, our SOA is the cobalt-2, and our SRA is the solid lead. So my two half reactions, we have cobalt-2 being reduced to form cobalt solid, and then lead solid oxidized to form lead-2. Electrons cancel, and we get our net reaction. To draw a diagram, there's two main distinctions between the voltaic and the electrolytic. So one is that we don't have that physical boundary. We don't have a salt bridge or a porous cup. Both electrodes are in the same solution. The other distinction is that we have to show an external power supply. We have to include the battery. Another way of demonstrating this, and you might remember this from like junior high when you learned about electricity. The symbol for a battery is one long line and one short line. So if you show on the wire that we've included a battery, this is the external source of energy. It doesn't matter which one of these you label as the cathode or anode because they're both solid lead, but it's important that we indicate the direction of electron flow and the direction of the ion flow. So that's the same between voltaic and electrolytic. That part doesn't change. So if we call this our anode and this one our cathode, the electrons flow from anode to cathode. Cat ions, so positively charged ions, flow towards the cathode, and anions, negatively charged ions, flow towards the anode. If we take the cell potential, so we have negative 0.28 for the cobalt reaction and negative 0.13 for the lead half cell reaction, we get our overall cell potential to be negative 0.15. So negative tells me it's non-spontaneous. The third part of the question asks, what's the minimum voltage that has to be applied to the cell to make it work? So in other words, how much energy does this battery have to supply in order to force this non-spontaneous reaction to happen? So if my voltage is negative 0.15, I need to provide at least 0.15 volts of energy to force this reaction. On the following page of your workbook, there's a summary for analyzing electrolytic cells. So again, the diagram, the two main distinctions is we have our battery and we have one solution, so we don't have a physical boundary. Next example, an electrolytic cell is set up with a power supply connected to two nickel electrodes, and it's immersed in an aqueous solution containing cadmium nitrate and zinc nitrate. Predict the equations for the reaction at each electrode and the net cell reaction. Also, calculate the minimum voltage that must be applied to make the reaction occur. So here's all the entities that we have present in solution. And if we take a look at our redox table on page 7, we can identify that our OA is the cadmium-2 and our RA is the nickel solid. So here's my two half reactions, including the cell potentials. Electrons gained equals electrons lost, and we get our net reaction. So the next part of the question is to calculate the minimum voltage that has to be applied for this reaction to occur. So if we take the cathode minus the anode, I have negative 0.4 minus negative 0.26, and we get negative 0.14. So this is a non-spontaneous reaction. So we require an external source of energy, and that battery has to provide at least 0.14 volts of energy to force this reaction to take place. If we were to draw this cell, we would have one solution containing two nickel electrodes. So these are both nickel. Our connecting wire contains the external power source. And then you could identify which direction the ions flow. So I'd have cadmium-2. If we called this the anode and this the cathode, the cadmium ions would flow to the cathode. The zinc ions would flow to the cathode. And then our negative ions that we have present, so the nitrate, oh, sorry, run out of room here. The nitrate would flow to the anode. Electrons go in the same direction from the anode to the cathode. Okay, take some time now to work through the practice problems. So question 1 is just like the examples that we just did. So we're predicting what the half reactions are at the anode and cathode, and then what's the minimum voltage that's required in order for those cells to react. Question 2 is just asking you for what that minimum voltage is. So we just need to identify the cell potential at the cathode, the cell potential at the anode, and take the difference. Questions 3 through 7 are short answer questions. Question 8, you're identifying, will these cells produce a spontaneous reaction or non-spontaneous? And then for question 9, again, we're determining the minimum voltage. Question 10 is asking you to draw a diagram. So just remembering what's the difference between the voltaic and the electrolytic. The difference is the porous boundary, and the electrolytic cell needs an external source of energy.